So today I plan to do propagation perpendicular to the magnetic field, which means the K is perpendicular to the wave propagation direction is perpendicular to B naught, which means theta is equal to 90. So basically these values I have to put now for sin theta and cos theta. So before I go to this stage, propagation perpendicular to the magnetic field, I would like to quickly do a summary of what we did last class. So basically, last time what we did was waves parallel to the magnetic field. So I just quickly summarize what we did last time. So in that case, we had put the value of theta equal to 0 in these equations and then simplified them. And then we got that there were three types of waves. The first wave was basically the wave vector is along the field line, along the propagation which is again parallel to the wave. So this was one of the waves, and the dispersion relation was basically omega square is equal to omega b square. So basically this is electron oscillations inside the plasma, and in cold plasma this doesn't it's not a wave actually, because it's a fluctuation or oscillations taking place at a given location in the plasma. So it starts transporting energy, or a wave starts propagating only when you consider warm plasma. Cold plasma you will not be able to, these will be just oscillations at a given position inside the plasma. So unless you go for warm plasma, where warm in the sense temperature is now high, which means gradient of pressure we have to put in the equation. We had neglected gradient of pressure. So that basically if you put, then you'll see that these wave oscillations will start transporting energy into the plasma, which means there's a wave propagation. But for the present case, let us say that because we are considering only cold plasma, it's just an oscillation, electron plasma oscillation at plasma frequency. So Ne squared by 4m. So that is the frequency at which it oscillates. And that is parallel to the E was parallel to A. Whereas the second case you will get two waves, and so their transfers to K, which means E is perpendicular to. So in this case, we got two waves, and one wave was called the R wave. We got the dispersion relations when we, so that was basically transfers right hand circularly polarized wave. Polarized wave. So this was one of the waves that we observed, and then that Also, we got the angle of polarization, the direction of polarization, which was given by putting eta square equal to r. So that was basically Ex by Ey. This was actually minus I. So this is the direction of polarization. So basically, if you are observing the wave coming towards you, the electric vector rotates in the clockwise direction. Actually, it is in the same direction as the electrons. When there is a magnetic field, electrons will gyrate. So it is actually in the same direction. So the polarization of this and the transverse right hand circularly polarized wave, so you can call it RCP. So that basically matches with the electron gyration around the magnetic field. So basically you can couple this energy to the electrons. So that is how you can heat the plasma. Heat the plasma electrons using this wave. So that was one of the waves. The other wave that we saw was again transverse, but that was left polarized. So left hand circularly polarized wave. You can call it LCP. So again for this we got the direction of polarization by again putting n square equal to L. So by that we got Ex by Ey equal to I, which is in the anti-clockwise direction. Earlier wave RCP was basically in the clockwise direction, and this is in the opposite direction. So basically this will match with the ion, not the electron, but the ion. Ions will now, if there is a magnetic field, ions will gyrate in this direction. So this wave can also be used for coupling energy to the ions of the plasma. So you can heat the ions. The earlier wave, which was RCP, it could be used to heat the electrons. This can be used to heat the ions in the resonance condition. So also we saw that both these waves had cutoffs also. We'll see where the cutoffs were and where the so we also saw last class that this NCT wave, the left and polarized, circularly polarized wave, had a cutoff, which means eta is 0. The refractive index is 0. So that we got for putting L equal to 0. And therefore this happens at a frequency called so this is the cutoff frequency for the LCP. Similarly, we had also seen that RCP, which means the right circularly polarized wave, had a cutoff at another frequency, which is omega 02, which is instead of minus, it will be plus the same thing. So basically you'll see that this is equal to nothing but omega 1 plus this cyclotron frequency. So this is much higher frequency than this. This is electron cyclotron frequency plus this frequency. So it has a cutoff at this point. So any this wave will have a cutoff. So which means it will not propagate at frequencies more than this. Okay. Also we saw that it had this was cut off. It also had resonances. So it had resonances at so RCP, the right circularly polarized wave, had a it's also called the electron cyclotron wave. And omega is less than electron cyclotron frequency. So it's called electron cyclotron wave. And similarly, LCP is called the ion cyclotron wave. And omega is less than omega Ci. So ion cyclotron frequency, electron cyclotron frequency. So it's nothing but EB by N. You have to put the charge. If this was minus, you will have EB by this was electron mass, this is ion mass. So because of this mass being very large, the frequency will be very small. So typically these frequencies are in megahertz, whereas this is in gigahertz because of the mass. So therefore, now also we told that there's a resonance, so you can use this wave to heat the electrons, and this wave you can use for heating the ions. So that is how these waves become important. So this is what we had done last class. So this was a summary of what we did last time. So today what I would like to do is consider the case propagation of waves perpendicular to the magnetic field. This was perpendicular parallel to the magnetic field. So basically you have to put this is perpendicular to B naught. So therefore theta is 90 degrees. So put this value for cos theta sin theta. So this whole thing will reduce. So we'll see how this gets reduced. So basically, I think I will write it again. So now today we are considering waves propagating perpendicular to the magnetic. So after we put those values for theta equal to 90 degrees, and then simplify for sin theta, cos theta, what you get is S so very simplified now. So this is the system of equations now. So let us try to find solutions of this system of equations. So one is the trivial solution, which is E's are equal to 0. But this is not what we are interested in. We are interested in non-trivial solutions. So those solutions are basically E, E tilde not equal to 0. E tilde not equal to 0. They are the non-trivial solutions. So that those non-trivial solutions basically come out from the matrix. This 3 by 3 matrix. We'll have to now get the determinant of this and make it vanish. So when you do that, you'll observe two independent modes of which propagate in the plasma. One is not equal to 0, non-trivial solution. This is O actually. Another wave we have X. I'll tell you what O and X mean. So the electric vector of the wave parallel is not equal to 0. Here the perpendicular component is not equal to 0. So these are the two waves. Let us see what these waves are. We'll have to put back the term what is P and R, L and S. So then when you put that, you'll see that the first one, I think I'll drop this off. So this becomes 1 minus x by u. Now again putting the values for x and u, you'll see that this is equal to 1 minus omega p e squared divided by omega squared. And we have assumed that there are no collisions. If you put collisions, there will be some modifications of this whole frequencies. So we are, for the case where you have no collisions inside the plasma, you'll see that these modes, this is one of the modes, and this is called an ordinary mode. We'll see why it is called ordinary mode. The other one is called extraordinary mode. So this is called ordinary mode because, see, what is happening is now E tilde is actually parallel to the magnetic field, which means if you in this quantity, if you take the tilde part of u velocity, that will get influenced by the electric field. So therefore, this will be parallel to the magnetic field. So this term goes to 0 because u is in the same direction as the magnetic field. So this quantity goes to 0. So therefore, this wave electric field is basically parallel to V naught, and so therefore there is no influence of the external magnetic field on the wave. The wave will propagate as if there was no V naught at all. The wave will propagate as if V naught was 0. So that is the reason why it is called ordinary wave. And this ordinary wave is also called O mode. O mode propagation or O wave, ordinary wave. Okay, this was one of the waves. So let us see what are the characteristics of this wave. So it's called ordinary because there is no influence of magnetic field external magnetic field on the wave propagation. So it will propagate as if B0 is 0. This wave is also called sometimes TEM mode, transverse electric magnetic mode, because both E tilde and B naught are perpendicular to K, transverse to the wave propagation. And these waves are linearly polarized. You can get it from Ex by the ratio of Ex by Ey. You'll find that earlier case we saw that it was a circular polarized wave. This is a linear polarization, linearly polarized. So this is about the one of the waves, which is the O mode. Let us see what happens to the other wave, extraordinary mode. So here the E tilde, the electric wave vector of the wave, so this is not equal to 0, so non-trivial solution. This is called the extraordinary mode. Because now U naught is U tilde is basically perpendicular to the magnetic field. So therefore there is influence of magnetic field. Because there is an influence of magnetic field, it depends on the magnetic field. So it's called an extraordinary mode. So the dispersion relation you can write down. So, dispersion relation we can write it down as RL by S. So basically you have to substitute these values, which basically is 1 minus x u by u square minus y square whole to the power of minus 1, 1 minus x u by u square minus y square whole square minus xy by u square minus y square. So that is the basically the dispersion relation for the extraordinary mode. So after you do all the substitution for x, u, and y, we'll write down what it how it looks like. So this equation now we'll put back all the factors and we'll see that theta square is omega square minus omega CE omega minus omega p square, and then you have another term which is omega square minus omega CE minus omega p square. This whole thing divided by omega squared Actually, this you can write it in a compact form, which is omega square minus this is what this is the frequency that we got last time for the cutoff for LCP lane. And this was cut off for RGP lane. Here I have written down omega UH, where basically this is called the omega UH is basically the upper hybrid wave. Hybrid frequency, which is defined as omega P square plus omega C square. Root of that. So upper hybrid frequency is given as this. So basically we have this is the term that we get here. So instead of that we have written down the upper hybrid frequency. So this extraordinary mode is also called TM mode because of transverse magnetic. Because the magnetic perturbations are of the mode is perpendicular to the wave propagation. And these waves are basically elliptically polarized. The earlier case we had linearly polarized wave. This is if you basically you have to do x by ey. So this will give you certain terms. So that will tell you whether it's a circularly polarized wave or a linearly polarized wave or a elliptically polarized wave. So TM mode is a very interesting mode. Very in most of the labs, these waves are basically used for doing lots of things. Sometime later, I can tell you what exactly you can do with each of these waves. The earlier waves I told you, you can use them for heating the electrons and heating the ions. So electron cyclotron wave and ion cyclotron wave. Now let us see the cutoff and other properties of these waves. Something like this out. All this information is there on in that book by Bittencourt. So basically go through it. As I told you, algebra is little cumbersome but quite straightforward. You can easily derive all these equations. In this book, it is given much better than many other books. Crowell and Trevor piece, also there's a book which gives you a lot of physics part of it, but then the mathematics becomes a little more involved. You'll not appreciate that. So you can do one thing, go through this part in Bittencourt, and then you can actually go through Crowell and Trevor piece. Of course, Crowell and Trevor piece is basically a book meant for research people. So more physics and more information. It's not just a derivation of the waves. So in that sense, it's interesting to go through that book. But then the way it is dealt is quite complex. So better go through Bittencourt first and then go to Crowell and Trevor piece. So the ordinary wave mode has a cutoff. equal to 0 at omega is equal to omega p. It has a cutoff, but there is no resonance. You could see from the expression itself. Resonance के लिए this has to go to infinity. So there's no way the refractive index can become infinite. If you see from the expression that we wrote for the ordinary wave. Whereas the extraordinary wave has a resonance, the E mode, extraordinary mode, has a resonance that is equal to infinity at the upper hybrid wave, that is omega UH, the frequency that we wrote before. So the extraordinary mode has a resonance. So you can again use this for heating both electrons and ions. So this wave becomes quite practical. And there's a cutoff. This was resonance. It also has a cutoff, which means the waves will not propagate for that particular condition. So it has a cutoff at frequencies which we wrote as omega 1 and omega 0 2. There are two frequencies that we wrote, in our earlier classes. So at these two frequencies, you'll see that the extraordinary mode has a cutoff, which means it will not travel. It will not. So there's the amplitude will decay exponentially inside the plasma. So which means it cannot transport energy into the plasma. So it has resonance and the cutoff also. But when you actually, in all these equations, what we have done is we have neglected the motion of ions. We have taken only the motion of the electrons. If you put in those equations for motion of the ions, you will see that the extraordinary mode, E mode, has a resonance. At frequencies so electron cyclotron frequency, ion cyclotron frequency. So therefore, it has a resonance lower than the upper hybrid wave, and this is called the lower hybrid wave. The earlier one was upper hybrid wave, and this is called the lower hybrid wave. And the frequency is given as omega c into omega ci. So it's basically geometric average of the electron cyclotron frequency. See, electron cyclotron frequency is in gigahertz, 10 to the 9, whereas this one is 10 to the 6. So this will fall somewhere in between. So you'll have a resonance at frequencies just geometric. You can take the square root of that, so it will give you exactly this. Suppose this was 8, 14, 10 to the 7. It will be in between those two frequencies. So that is how you get resonance at lower hybrid. You got lower hybrid, upper hybrid, and then you have got electron cyclotron wave, electron ion cyclotron wave. So I think this much for today. Next class, basically, we'll go for this CMA diagram. Basically, you can put all this information into a graph x versus y, where x will be x direction. You have the um, plasma density varying, and in the y direction you have the magnetic field varying. So it is something like a total picture of the plasma. So that diagram is very, very important. So I would like to spend full class on that. So CMA diagram, basically it's very complicated diagram because it's broken up into 8 different regions where you describe all these waves which we discussed these 2 days, and you can get the information about all the cutoffs and resonances for each of these waves, and also you can know when these waves propagate and when they get highly attenuated. Also, you'll see that a wave enters into the plasma, it immediately vanishes, and after certain frequency again it reappears. So all these information you will get in the CMA diagram. It's a very interesting diagram. Essentially, I'll just tell you what I'll not get into too much of details about this today, but then next class, CMA diagram. What you're doing is this is the x direction, this is the y direction. So what you are plotting is omega c square by omega square, and this in this direction what you are plotting is omega p square by omega square. Omega p square is basically n e square by m. So basically electron density. Essentially you are drawing along the density. Whereas here this is the cyclotron frequency, which is EB by m.
Hello. Hello, students. Can anyone hear me? Anyone can reply?
Yes,
Yes,
sir.
sir.
Yes, sir.
Sir has just lost the connection, so please wait for 2-3 minutes to rejoin. Right?
Okay, sir. Okay, sir.
એટલે કુલદીપ સર બેઝિકલી એ એનું કેલ્ક્યુલેશન So what you will do is you will take the dot product of this vector on this axis. तो तुम्हें जाने अब अपने एक्सिस में आनु dot product LZ dot Z. So this will actually give you this projection of this vector on this direction. हाँ ये dot है and G equals to 0 and Z equals to 2. I know is under root of L into L plus 1. ठीक है अब जो तुम्हारा L is equal to 2 है तो શું થશે under root of 2 into 2 plus 1 तो root 6 અને એ एक्चुअली માં આ એક થોડા નાના નાના ફોર્મ્યુલા છે આ બધું છે ક્વોન્ટમ બાજુ જતું રહે છે અત્યારે આ જે છે ને જો ક્વોન્ટમ મિકેનિક્સ जनरली इंडिया શું मतलब કે હવે મને ખબર નહીં આપણે શું કહે but quantum mechanics has been a very successful theory for the past 100 years હવે આ કોઈ modern physics નથી it has become part of every physics and it is relatively very old એના માટે બધું કરવું જ પડે એટલે this should be taught although આપણે હવે એટલા મેચ્યોર થઈ ગયા છીએ અહીંયાનું કરિક્યુલમ પણ कि क्लासिकल मिकेनिक्स થી પહેલા આપણે ક્વોન્ટમ મિકેનિક્સ આપણી કોલેજમાં પણ ઇન્ટ્રોડ્યુસ કરી દીધી છે તમે પણ ભણ્યા છો તો થોડું ઘણું તો ક્વોન્ટમ મિકેનિક્સ તમને ભણાવ્યું છે પણ ક્લાસિકલ મિકેનિક્સ તમને નહીં ભણાવ્યું તો થોડું મેચ્યોરિટી તો આવી છે બટ ક્વોન્ટમ મિકેનિક્સ ટુડે ઇઝ ઇન સોલિડ સ્ટેટ ફિઝિક્સ ઇટ ઇઝ ઇન લેઝર્સ ઇટ ઇઝ ઇન એટોમિક ફિઝિક્સ કોસ્મોલોજી को કે શું પણ को સાચી વાત છે આ એક્ચ્યુઅલી માં ફોર્મ્યુલા આવ્યો છે કે આ જે તમારું વેવ ફંક્શન છે ને psi when this operator LZ operates on psi, then the answer will be under root of L into L plus 1 H cross into psi again. આ જે તમારી છે ને આઇગન વેલ્યુ છે હવે જે તમારું L is equal to 2 હોય then LZ when operate on psi will give you root 6 H cross psi. So this is actually the measurement of LZ on the wave function and what is your result it is root 6 H cross any value like to L ની value sorry L square ની છે L ની છે actually માં કેમ કે આપણે L square નું કરીએ છે ત્યારે L into L plus 1 લઈએ છે તો આ L square is equal to એવું હોય છે psi is equal to under root of so L into L plus 1 હોય છે okay H cross square into psi હવે આ તમને L square જ્યારે આવું છે તો L તમે કેવી રીતે લેશો under root of L into L plus 1 લેશો H cross
एक्सक्यूज मी सर.
હા બોલો દર્શન.
સર આવવા નથી.
આવવાના છીએ, એમને કંઈક પ્રોબ્લેમ આવ્યો છે ઇન્ટરનેટ
ઓકે
કનેક્ટિવિટી.
ઓકે ઓકે ઓકે.
Hello, Birin.
Yes, sir.
You're able to hear me?
Yes, yes, I am able to hear you. You can continue, sir.
Actually, I don't know what happened. Suddenly,
No,
this went off.
no problem, sir. You can continue.
So I can continue.
Yes, sir.
Okay. Okay. So the syllabus part is over. So what I would like to speak today is about the neutrons. See, neutrons are actually very close to my this one because right from my MSc days. See, MSc I got in nuclear physics, MSc in nuclear physics with specialization in neutron physics and reactor principles. So, therefore, I would like to talk a little bit about what these neutrons can do with respect to both fission, fusion, or in general artificial radioactivity. So, actually, that is my field. So, neutron physics basically, I'll show you how they are useful. See, these neutrons, because they are chargeless, they could easily walk into any nuclei, heavy or light, whatever. So they can just get into the nucleus and make it radioactive. So any material you take, whatever material you can see in front of you, I can make it radioactive by bombarding it with neutrons. And neutrons can do it very easily because it has no charge, so it doesn't suffer with that Coulomb barrier. See, any charged particles like protons or alpha particles or neutrons, tritons, these particles will have problem to cause a nuclear reaction because the moment they try to enter into a nucleus, you'll see a huge barrier. It's like a hill. It has to cross that, only then it can get into the nuclear potential and start nuclear reactions. Whereas a neutron, because it has no charge, so no Coulomb barrier for it, it just enters into any nuclei and it converts a stable nuclei into a radioactive nuclei, which means it makes it unstable. So then it starts emitting various radiations, nuclear radiations like um, gamma rays, beta rays, alpha particles. So, so that is the advantage of using neutrons. See, any material I can activate by bombarding it with neutrons. So once it becomes radioactive, it starts emitting radiations. So these radiations can be used to measure various things, like how much of radioactivity has been produced. So that kind of information. So it's called neutron activation analysis, which is I'll come little later. But let us see how neutrons play a role in both fission and fusion. The fission, there's a heavy nuclei. So a slow neutron enters into it, like uranium. It enters into that and disturbs the whole nucleus. Then the nuclei breaks up into two. So that's called fission. Fission processes, heavy nuclei will break up into two nuclei, and then in that process it emits more neutrons and energy. So that is how uranium 235 is one of the fissile nuclei. So it's a fuel. So this plus neutrons, it produces fission. You have the whole nuclei gets broken up, and then so this is the fission process. So you can see that a neutron which has zero energy. See, what are these neutrons? They are slow neutrons or thermal neutrons. Thermal neutrons, their energy is how much? 0.025 eV. So this is almost zero. So zero energy neutrons can just coolly enter into a nuclei of uranium-235 and cause fission. And fission means lot of release of energy. So that energy can be used for peaceful purposes. It can be used as weapon and thing, anything, depending upon your usage. So imagine a neutron with just zero energy is able to do so much of damage, so much of modification. I will not say damage, so much of modification. So it can release a lot of energy. This energy can be converted into electrical energy. So that is how the nuclear energy, that is, you get nuclear energy from fission. So that is the role of neutrons in fission. And in fusion, what is happening is the fusion reaction is taking place between deuterium and tritium. They are the heavy isotopes of hydrogen. So this leads to alpha particles plus neutrons. So now you'll see that the energy of it's an exergic energy. Look, there's a positive energy coming out. Q value is positive. So you have this plus lot of energy coming out. Q value. And this is typically Q is 17.6 MeV. So this huge amount of energy is released after this deuterium and tritium fuses together. So it produces alpha particles and neutrons. Now you just see that this 17 MeV has to be shared between these two particles, alpha particles and the neutrons. Now because neutrons are lighter than the protons, uh, lighter than the alpha particles, 4 times lighter. So what will happen is most of the energy is taken away by the neutrons. So in fusion process, what is happening is most of the fusion energy actually is in the neutrons. So you have to be an expert in neutronics, study of neutrons, to be able to extract this energy, fusion energy from the neutrons and convert that into electrical energy. So you will see that neutrons are playing huge role between in the fission and fusion process. Not only in these two processes, I told you in general, any stable element, you can produce artificial radioactivity in them just by passing neutrons into them. Why is it doing? How is it doing it? So you know, if there's a nuclei, so what is happening is you have a nuclei which has number of neutrons and protons. So there is some ratio of P by N. But I can change this ratio by adding more and more neutrons. Once I do that, this nuclei becomes unstable because mass is increasing by adding more and more neutrons. And when you add more and more neutrons, the whole material the nuclei becomes unstable to beta decay. So immediately that nuclei will decay to a stable position if I keep on adding more and more neutrons. If I keep on adding more and more neutrons, what the nuclei will do is it will emit betas. So, and then it will relax back and get rid of this extra neutrons that have been added. So that again it gets back to N and P ratio. So that there is a stability of the element. So against beta decay. So what is happening is basically if you draw number of neutrons versus number of protons. you'll see that there is a line. It's called beta stability line. The moment you start deviating, either going this way or this way, you'll see that these nuclei will become radioactive and they will somehow get back to this. So stability, it has to gain stability. Either I can increase the number of protons, I can increase number of neutrons. See, increasing number of protons is difficult because proton has a charge. So I told you, proton when it has to enter into a nuclei, it has to have that extra energy to overcome the Coulomb barrier. Whereas the neutrons, because they are uncharged, they can just enter into any nuclei. So I can produce more and more nuclei which are neutron rich. So they become so radioactive, they start emitting lots of alpha particles, betas, gammas, and all. Then finally, it will come back to this line. This is called the beta stability line. So, because of this reason, the more number of neutrons you keep adding into a nuclei, the stability is lost and they become radioactive. They start uh, pushing out particles from the nucleus so that they can gain stability. So there is a, because of this activity of the neutrons, that any material I can take and activate it, this is called the neutron activation analysis. Neutron analysis technique. I'll explain to you more detail how, what exactly is this technique, and a very versatile technique. You can use this for any field, in agriculture, medicine, whatever. I cannot name it. Anything that you name, you can produce. So the technique is basically that you start with a target, any target which has some A and Z. So target any nuclei which has mass number and proton number, atomic number. So what you will do is you will irradiate that with neutrons. The neutron has zero charge, mass 1. So when the neutron gets absorbed into it, it forms a compound nucleus. Compound nucleus. Basically, a neutron gets absorbed into it, and then from the ground state, it goes to a higher excited state. So this state, energy is given by the amount of kinetic energy and binding energy that the neutrons are bringing. So total excitation energy, this is excitation energy, Ex. So this Ex is basically the kinetic energy of the neutrons plus binding energy. So binding energy typically what 6 MeV. For I'm taking average over the whole periodic table. So this is fixed. Whereas kinetic energy, I can start with, as I said, thermal neutrons, which means zero energy, 0.025 eV. So you'll see that if I add 6 MeV to this, it is just 6 MeV. This is almost zero. So the excitation energy is now 6 MeV. So now this, because it is excited state, it will now emit beta and then come to a residual nucleus. This was compound nucleus. This is the residual nucleus. So this is the ground state. So now there are lots of betas coming out from this, So beta 1, beta 2. So from here you will have gamma emissions. So now the technique is basically take any target, bombard with neutrons, produce compound nucleus that will decay through beta and then gamma. So I can use these betas or the gammas. I put detectors to measure this, and then I can get a lot of information about the target or how much neutrons were hitting, all the details. So basically the amount of reactivity is n, phi and sigma. This is the number of nuclei of this. Whereas and flux, this is number of neutrons. This is flux of neutrons. And this is the cross section. Cross section for this particular reaction to take place. So now you can imagine instead of a thermal neutron, if I take high energy neutrons like 14 MeV neutrons, they are the energy that the 14 MeV neutrons are the ones which are coming out from the fusion reaction. So if I use those reactions, you'll see that the excitation energy I can produce is 6 plus 14, but typically 20 MeV. So now 20 MeV is far beyond. So I can produce more and more activity. I can get more number of gammas, more number of residual nuclei. So I can do this whole technique more efficiently if I use high energy neutrons. So that is what is the whole technique. Use the neutrons to bombard targets, produce betas and gammas. I can measure them. By measurement of this, I can tell lots of things about either the number of nuclei present in the target or the flux of neutrons falling on them, or I can measure the cross section. So I had used this technique in my PhD to measure the cross sections. So my idea was to get the cross sections for various elements. But if I know the cross section, I can calculate, I can get the number of nuclei of this. So I can take any sample related with neutrons and try to get the information about the material that was irradiated. So this is a very, very powerful technique. See, by this technique, people had come to know that Napoleon was actually food poisoned. He died of food poisoning. How did they come to know? So from the museum, they had the hair of Napoleon. So that hair was irradiated with neutrons. Then it found out all the elements present inside the hair. Because you can get the full details about everything about this target. So this target could be anything. Napoleon's hair or somebody's nail. So this can be used in forensic sciences. I can do neutron activation analysis and get all the information about how the patient died, whether he was poisoned or not poisoned, or lots of details about the whole process. So this is application to forensic science, but it can be applied to any technique, Like for example, ONGC does a lot of activity on soil to find out the quality of oil. So unless they are confirmed about the quality of the oil, they should not do a well rigging, because you'll be wasting your efforts and money if you do a well logging where you don't have a very a good quality oil coming out from there. So all that information you get from the soil. You can take samples of the soil and do neutron activation analysis. That will tell you the full constituents of the soil. So therefore, I can know what will be the quality of oil that I can get. So that is how ONGC uses this information. You can do a lot of things like aerosol. I can get samples of aerosol and find out what are the pollutants by doing neutron acquisition analysis. So it's a very, very powerful technique. You can do a lot of basic research like I did for my PhD, measure the cross sections. So my interest was to measure cross sections for materials which are used in fusion as a construction material in fusion reactors. Then I studied what are the effect of neutron bombardment on them, what kind of radioactivity is produced, what are the various types of reactions produced by the neutrons. So all those details, what kind of damages are produced by the neutrons. See, because neutrons have, it is like a billiard ball. So billiard balls with brute force, it can enter and destroy the whole nucleus. It can displace the crystal structure and things like that. So that is how neutrons damage materials. So it's a very, very big issue for fission and fusion both. Fission may, of course, the problem is not that great because the neutron energies are low. Whereas in fusion, the energies are very high, 14 MeV. Whereas in fission, it is typically 2 MeV. So not that much of damage. Here in fusion, the neutrons produces much more damage. So it can be catastrophic sometimes. Any material that you have taken to build the reactor component, it will get destroyed in no time. So you have to know what materials to be used. So you have to do a lot of neutron analysis of that. Or in the experiments, you irradiate with neutrons and try to understand how the various elements or materials behave in the flux of neutrons. How much of damage is produced, whether it's a good material to be used in construction of a fusion reactor or not. It's a very interesting thing that comes out from the study of neutrons. So this is the lab that we had in IPR. So this was the activity which I started in IPR. The moment IPR started working on fusion, so I saw that the materials have to be now tested for 14 MeV neutrons. So what I do is I produce 14 MeV neutrons. So these are the energy neutrons which are produced in fusion reactors also. So I can produce in the lab by some different method and use the same neutrons to do a lot of studies, nuclear studies. Same thing I can extend it to plasma physics also. So when such neutron, some neutron bombarded material is there, present very close to the plasma, how plasma gets affected. So that is the study that I did in IPR. So very interesting. I'll send you some information on what kind of activities are going on in IPR related to neutronics. This whole field of activity is called neutronics. Because for fusion, fission, everywhere, neutrons are playing a role. So therefore, you have to do a lot of study of materials. And believe me, fusion will be successful only if you get right kind of materials. If you don't get good materials which can withstand this neutron bombardment, you'll never be able to successfully have fusion reactors. Because any material that you take will have a lifetime now. They are not they are not present, they are not having life for say 40 years, 50 years. Their life will be reduced to just 5 years because of this neutron bombardment. So a lot of research is going on what kind of damages are produced by the neutrons to the materials. So full physics study of neutron damages and how to control this damage. So you have to come up with very innovative ideas for materials. So there are some materials called self-healing. They have self-healing properties, So even if I do some damage by neutrons, it has a mechanism by which it can heal itself. It's called self-healing materials. So there is a lot of study going on in this material science, computational material science, Very, very interesting field. I'm sure many of you will be interested to get into such areas of research. Material science is going to be a very, very useful area where most of the new technologies like fast breeder reactors or fusion reactors will need this study to come up with ideas about good materials, how to make materials smart, smart materials which can heal itself during the process. You don't have to remove them from the system. While the process is going on, it has a mechanism by which it can recover from the damage that the neutrons have produced. So this field has become very interesting now. And we did a lot of work in IPR. I started a division called Fusion Neutronics. So if you people happen to go to IPR, you can visit this lab, Fusion Neutronics lab. They have very good sources of neutrons to do a lot of these research activities, to come up with better and better materials and to understand what kind of damages are produced by the neutrons. So very interesting study. Also, when I told you about fusion reactors, I told you most of the energy of the fusion is in the neutrons. So I should be able to extract this energy from the neutrons. So for that, I should be a very good neutron physicist. How to extract this energy from the neutrons? What materials to use where the neutrons will deposit its energy, and that deposited energy can be converted into heat. So it can be converted into, sorry, what was I saying? So materials, is going to some, now I was talking about in fusion, the most of the fusion energy is in the neutrons. So you should be able to extract this energy from the neutrons, produce steam to run the steam turbine, and that is how you can produce electrical energy from fusion reactors. So for that, I should have a very good knowledge about the neutrons, the neutronics part, neutron physics part, so that I'll know what materials to be used to extract this heat from the neutrons. So this is a very interesting field of research, and I have spent all my time on this doing fusion neutronics. So anyone interested, I can share a lot of information. And right from my MSc days, MSc itself, I had Neutron Physics as one of my uh, specialization. So in my MSc and PhD type, I was from the fission reactions. Then when I joined IPR, I started doing fusion. So I have exposure to both fission and fusion. So anyone interested in discussing any of these topics, I'll be very happy to do that. Okay, I think I'll stop here. So this is a area where you can do a lot of research, and plenty of research is going on even today. Lots of new labs in the world are coming up doing neutronic studies, because neutrons not only in the field of energy, also as I told you, these high energy neutrons are also used now in cancer therapy. Something called boron capture therapy. Very interesting things are happening in medicine also. And starting point is neutrons. So someday I can discuss more about this, how neutrons are being used in medicine now. So I think I close here, and I am sorry for the short disruption that took place. Any questions or clarifications that you need, please give your feedback. Any one of you? Any questions for me?
Hello.
Yeah. Yeah, Heath, Bolly.
Sir, I want to ask you something. Sir, how did
Bolly.
you came to that decision that you want to do PhD in this particular subject? Means there
Oh,
are a lot of subjects. Then how you decide at
okay,
that point?
okay. A good question. See, as I told you, my MSc was in nuclear physics. MSc degree in nuclear physics with specialization in neutron physics and reactor principles. That was basically fission reactors. So that was the study that I did for my MSc. And then we had a lot of experiments with neutrons during our MSc course. So somehow neutrons, I was really enamored right from my MSc days. So I just somehow wanted to get into this area and do some research leading to either understanding the fission process. I never thought I'll work in fusion. Though I had used 14 MeV neutrons, I generated 14 MeV neutrons in my lab, my MSc, the PhD lab, and then see there was a small particle accelerator is required. You have to accelerate diatron beam and then hit it on a tritium target, and then there is a nuclear reaction taking place, DT reaction. Same DT reaction takes place in the lab also, and that produces 14 MeV neutrons. So those 14 MeV neutrons I had used for my research work. So that time somehow towards the end of my research, I got a somehow I got a one of the conferences going on in Europe where I came to know that some of these cross-section measurements of 14 MeV neutrons on materials of fusion materials will be of use. So somehow then I converted my whole PhD into materials which are useful for fusion reactor design. So I took all materials which are required for constructing a fusion reactor and study the neutron bombardment on them. Trying to study the cross section for various reactions, and then to study what kind of damage the 14 MeV neutrons produces in these materials. And so that was what I did for my PhD. But I didn't work on how to, in case there are damages done by the neutrons, how to take care of them. So those activities I started in IPR. So after IPR became member of the ITER program. ITER, I hope you people know, ITER. It's an International Thermonuclear Experimental Reactor. So it will be the first fusion reactor being built in France, where they'll demonstrate the fusion power, fusion energy. So they are going to have this DT fusion, which I described to you. So in France, we are going to produce this DT reaction, have fusion. So moment you heat this, you take a mixture of deuterium and tritium, and then heat it to high temperatures. And when you heat it to very high temperatures, these particles will now overcome the Coulomb barrier. So they can enter into each other's nuclear potential and conduct a nuclear reaction. So that is what is happening. But when you do that, you're starting with a gas, mixture of two gases. But when you heat it to high temperatures, you'll see that this gas gets converted into plasma. So that is how plasma comes into picture. So now if I have to do fusion reactions, I should understand what is a plasma. So that is how I got into plasma physics. So without knowing this, I cannot get into fusion. Though I had knowledge about the neutrons, but I didn't have knowledge about when you take them, you mix two gases, deuterium and tritium gases. Deuterium, tritium, see, they're like hydrogen. Chemically, they'll be like hydrogen. Only physically, their masses are more. Deuterium has one neutron extra. Tritium has two neutrons extra. So it is heavier atom compared to a proton. Otherwise, chemically, they will behave like hydrogen. Chemically, there is no difference between hydrogen, deuterium, or tritium, because chemistry depends upon the number of electrons, not what is there in the nucleus. Because each one has just one electron in the atomic orbits, so the chemistry is same. Physics is different because this has one proton, this has two protons, one proton, but one neutron. It has two neutrons and one proton. So physically they are different, but chemically they are same. Did I answer your question here, Pete? Or so that was the reason why that's the reason why I took up
Yes, sir.
study of neutron bombardment on materials of fusion reactor interest. So that was my PhD work. Any more questions or clarifications you want? See, I want you people to interact more so that I can talk more. If I talk more, I can pass on more information to you.
Sir, I have
Please.
one more question. I want to
Yes.
ask you,
Yeah.
sir, during this all exercise, sir, you have to simulate these all things with computation. So, sir, what percentage you need for computation with a computer?
Oh, oh, very excellent question. See, I didn't tell you this part. And good that you have asked me this question. See, neutrons, one thing is production of neutrons are very expensive. Each neutron comes out with a lot of money. Not only that, if I produce neutrons and any reaction produced by the neutrons is going to produce a lot of radioactivity, so lot of radiation. So therefore, when I do a neutron experiment, before I do an experiment with neutrons, I have to do a lot of simulations. Simulations means I have to do a lot of Monte Carlo MCMP codes I can use and do a lot of simulations even before I go to experiment. So my PhD guide, will never allow me to go to directly the lab and start producing neutrons and start producing nuclear reactions because it's very dangerous. What I'm producing can kill some people if I'm not careful. So I should be doing experiments very, very carefully. So when I have to do careful experiments, I have to be guided properly by computation or simulations. I should know exactly how the experiment should be done so that little damage to environment or people around. Easily neutron activity is very, very tough because you need a lot of shielding, human shielding, because in addition to you, there are lots of other colleagues working around you. So you should not irritate them with neutrons. So I need the whole lab to be totally shielded so that no neutrons go out of my lab. So these are some of the interesting but difficult. See, doing experiments with neutrons are a little difficult because first of all, see, the moment you start say, okay, I want to do experiments with neutrons, you have to get clearance from the AERB, Atomic Energy Regulatory Board, that in my lab I want to produce neutrons. They'll come and supervise. They'll come and see whether your lab is good enough, well shielded. See, I myself should not get affected by the neutrons. No? So I should have a good knowledge about what happens to a human body when neutrons are bombarded, what kind of damage it does to various organs. So I should know all these details. Otherwise, I will be doing harm to my own self. Forget about others. So experiments with neutrons is very, very tough because the moment you say that I want to start neutronic activity in IPR, ARB people will come and check. They'll fully, thoroughly check your designs and see whether your lab is good enough for doing neutron research. So therefore, I have to be very good in simulations. Every neutronic experiment, I have to do lots of simulations before that to ensure that all my research doesn't produce any ill effects to anyone, including myself. So for that, a simulation has to be done for the whole experiment that is going to guide you how to do an experiment. So simulations is a very important part of neutron studies. Now it is becoming very useful even in plasma physics also. See, the whole tokamak experiment I can do by simulations. I don't have to go to a tokamak. There are computational codes available. I can do a simulation of the whole experiment. So in that experiment, I can understand all the physics. And then when I go to the actual tokamak, the experimental lab, I am already having a good knowledge about how to deal, how to do an experiment, both physics wise also, to get the maximum benefit out of an experiment. So simulations are very important part. Something called MCMP, Monte Carlo codes for neutral particles. A very, very important code which can be used to study. It's a Monte Carlo code. So you can use that code to do any type of simulations on neutron experiments. So in our lab, first of all, you'll do a MCMP simulation. Only then you'll be allowed to do any experiment. Because before you go to the experimental setup, you should know exactly what you want to do so that you don't waste the neutrons that you are producing. Also, those neutrons which are produced should not cause any problem for other members. Or in your own lab, it can destroy some of your things. If I have some sensitive materials inside my lab, the neutrons will go and bombard them and kill them. Those materials will not behave like, see, like I'm talking about detectors. These detectors are very sensitive. So these neutrons which are produced should not go and destroy my detectors. It will do material damage, which means the detector will no more act like a detector because it has already got material damage. So good that you asked me this question. Simulations is a very, very important part of neutron experiments. And now it is becoming useful for doing, see, it gives you a very good guidance how to do an experiment. So plasma physics is also done through simulations also. But वहाँ पे, see, the risk is not much. Whereas in neutron studies, this risk is too much because you're producing a lot of radioactivity. See, all the walls of the lab becomes radioactive after some years of operation of the neutron source. The walls will start emitting gamma rays. So you have to be very careful what kind of wall I should use, what material to be used in the concrete, so that it absorbs the neutrons and doesn't produce a lot of radioactivity. So right from construction of the lab itself, it is affecting your experiment, So that is how any activity of using neutrons, you'll have the Atomic Energy Regulatory Board people coming and helping you. They are experts of shielding and things like that. So you can do a lot of simulations and show to them how you're going to take care of all the risks that is available, is present with the neutron studies. Very, very interesting. Challenging but interesting. Yeah, any more questions? So if there are no more questions, I think we'll call it a day. So Biren, shall we close?
Yes,
Shall we
yes,
close?
sir. Yes, sir.
Oh, thank you, Biren.
Okay, okay, sir.
I'm sorry for the short delay.
No problem, sir. No problem.